Welcome to Mastering Solutions. So I've drawn the picture of our diverging mirror here, and remember the focal point for a diverging mirror is always on the right side by convention, and it's always going to be a negative value because of that. So we'll go with the question here. I'm going to calculate mathematically all this stuff, but just to show you what they wanted you to do, they say that we have this object here, right? And they tell us that the image is formed is 75% is tall. And so we have almost as tall, but not quite, about 3/4 or 75% of the way, like this. And so now we need to use ray tracing to figure out where the distance to the focal point would be for this mirror. I might move it just for the ray tracing. But what they wanted us to do is to draw this on like graph paper or something and draw it to scale so we can estimate where it's going to land. But remember, we'll do the 3 rays. We have parallel, and then it's going to go to the focal point. So yeah, I'll move that. So let's say right here is a focal point. And then we go through the center of the lens. And the angle of incidence is always equal to the angle of reflection. And then we have through the focal point and then parallel. And so it's going to go through the focal point and then parallel. And so we can use the height of the image here to guess where the light rays are going to all cross. So then we can see, okay, this one's going to come down to the focal point and this one's going to come to the focal point. So then we could say, okay, that's the estimation. So that's what they wanted us to do. And then if you were on graph paper, you could measure it and tell a value of where the focal point was going to be. And so now what is it that we are trying to find for this, right? We need to find the focal length. So if we were to do this mathematically, what we would do is we can use the relationship of h prime over h is equal to s prime over s. And so we would we want to isolate the image distance, right? Because we know how far away the object is. And so if we multiply both sides by, not s prime, by s, then we get s prime is equal to the object distance times the ratio of the image and object heights. And so now it doesn't really matter how tall the first one is, right? We just know that whatever the height is, this has to be 0.75 times that. It's a ratio. And so if we come down here and rewrite this, s prime is equal to the object distance, which we said was 12 centimeters, so 0.12 meters times a ratio. We could just say that h is 1 to represent 100%. And then the image height we'll say is 0.75 to represent 75%. So 0.12 times 0.75 divided by 1 gives us 0.09. So the distance is 9 centimeters, or the 0.09 meters. So that's how far away it is. So now we can use the thin lens equation to solve for the focal point. Now, this needs to be a negative 9 centimeters because the sign convention is that with a diverging mirror, all of the images are going to be virtual. And since it's on this side of the mirror, that means it's going to be negative. So now that we have the object distance, which we know is the 0.012, which we know is the 0.12 meters, and now we have the image distance, which we just found is the negative 0.09 meters. Now we can use the thin lens equation to solve for the focal length, right? So 1 over f is equal to 1 over s plus 1 over s prime. So 1 over f is equal to 1 over s, which we said is 0.12 meters, plus the image distance, which we said is a negative 0.09 meters. So we have 1 divided by 0.12 plus 1 divided by 0.09, and that's a negative 0.09. So we have negative 2.78, and that's diopters. That's 1 over f. So we need to take the reciprocal of that answer to give us meters, and that's 36 centimeters. So negative 0.36 meters, or a 36 centimeters is the focal point for this diverging mirror.